You're lying in bed, staring at the ceiling, and for just a moment, you notice how perfectly the shadows fall across the plaster. The mathematics of light and angle create precise patterns that your brain processes instantly, effortlessly. You blink and the pattern shifts with mechanical precision. Your phone sits on the nightstand, its screen dark but still humming with billions of calculations per second, rendering reality whenever you glance at it. And somewhere in the back of your mind, a question whispers, what if? Welcome back to Midnight Deep Dive, or if you're new here, welcome to our cozy corner of the internet, where we explore the biggest questions humans have ever asked. Tonight, we're venturing into one of the most mind-bending ideas in modern philosophy and science, the possibility that our entire universe might be a simulation, an extraordinarily sophisticated computer program running on hardware we can't even imagine. So settle into your most comfortable position, let your breathing slow and deepen, and join me as we trace this extraordinary idea from ancient philosophy through cutting-edge physics. Imagine you've lived your entire life in a cave, chained in place so that you can only look at the wall in front of you. Behind you, there's a fire, and between you and that fire, people carry objects that cast shadows on the wall you're facing. These shadows, flickering, distorted, two-dimensional, are the only reality you've ever known. You give them names, you track their patterns, you build your entire understanding of existence around these shadows. And then one day, someone breaks your chains and drags you out of the cave into the blinding sunlight. The shadows weren't reality at all. They were projections, reflections, illusions. Everything you knew was wrong. This is Plato's allegory of the cave, written around 375 BCE, and it might be the oldest ancestor of simulation theory. Plato wasn't talking about computers or programs. Those concepts wouldn't exist for another 2 millennia. But he was asking the fundamental question that still haunts us today. How do we know that what we perceive as reality is actually real? For Plato, the world we experience through our senses was like those shadows on the cave wall. Imperfect copies of a higher, more fundamental reality he called the world of forms. A beautiful sunset isn't truly beautiful. It's a flawed reflection of the form of beauty itself. A circle drawn in sand isn't truly circular. It's an imperfect copy of the perfect, abstract form of circle that exists in some realm beyond sensory experience. In Plato's philosophy, we're all cave dwellers, mistaking reflections for reality, never seeing the true nature of existence. What makes this ancient idea feel so modern is Plato's suggestion that there are layers to reality. That what seems fundamental might actually be derivative, that what feels real might be representation. If you've ever wondered whether you're in a simulation, you're asking Plato's question in digital terms. Is the reality I perceive the fundamental layer, or am I experiencing something generated by a more basic underlying system? Now let's travel east about a century after Plato to ancient China. The philosopher Zhuangzi, one of the founders of Taoism, told a story that has puzzled and delighted thinkers ever since. He dreamed he was a butterfly, fluttering through a garden without a care, completely unaware of being Zhuangzi. When he woke, he found himself wondering, was he Zhuangzi who had dreamed of being a butterfly? Or was he actually a butterfly now dreaming of being Zhuangzi? How could he know which reality was the dream and which was real? This wasn't just a playful paradox. Zhuangzi was making a profound point about the nature of consciousness and reality. If the experience of being a butterfly in a dream feels completely real while you're dreaming it, and the experience of being Zhuangzi when awake feels completely real while you're awake, what criterion can you use to determine which state is more real? Each reality is convincing within itself. Each consciousness is certain of its own existence in the moment. This idea resonates powerfully with simulation theory. If we're in a simulation sophisticated enough to be completely convincing, one that gives us consistent physical laws, sensory experiences that seem real, memories that feel authentic, how would we know, Just as Dream Zhuangzi doesn't know he's dreaming, simulated beings might not realize they're simulated. The very consistency and coherence of our experience could be evidence of good programming rather than fundamental reality. The concept appears across Eastern philosophy in different forms. Hindu philosophy introduces the idea of Maya, the cosmic illusion that veils the true nature of reality. The world we perceive, according to this view, is a kind of divine play or projection, not ultimately real in itself, but an expression of a deeper, unified consciousness. The multiplicity we see, all these separate objects and beings, is illusory. The fundamental reality is singular, undivided, beyond the categories our minds impose on experience. Again, notice the structural similarity to simulation theory. Both suggest that the reality we experience is generated or projected by something more fundamental. Both propose that our usual way of understanding existence might be missing crucial layers. Both raise the possibility that the distinctions and separations we take for granted might be artifacts of how reality is presented to us rather than features of reality itself. Fast forward to 17th century France, where philosopher René Descartes sat in a warm room, wrapped in a dressing gown, trying to find absolutely certain knowledge. Descartes decided to doubt everything he possibly could, to assume that anything that could conceivably be false was false, to see what, if anything, would remain as indubitably true. He could doubt his senses. After all, senses sometimes deceive us, creating illusions and hallucinations. He could doubt that the external world existed. Maybe everything he perceived was a dream. But then Descartes took his skepticism even further. He imagined an evil demon, a malicious entity of supreme power that was dedicated to deceiving him about everything. This demon could make him think he had a body when he didn't, make him think he was sitting in a room when he wasn't, make him think mathematical truths were true when they weren't. The demon could fabricate his entire reality, feeding him false experiences designed to fool him completely. Sound familiar? Descartes' evil demon is functionally identical to the hypothesis that we're in a simulation designed to deceive us about the nature of reality. In both cases, there's a powerful external intelligence creating the reality we experience. In both cases, that reality might be completely fabricated. In both cases, we're left wondering what, if anything, we can be certain about. Descartes' answer became one of philosophy's most famous conclusions: cogito, ergo sum, I think, therefore I am. Even if everything else was an illusion created by the demon, the fact that he was being deceived meant something was there to be deceived. The very act of doubting proved that a doubter existed. Consciousness, self-awareness, the experience of thinking. This seemed to be the one unshakable foundation. But even this foundation becomes questionable in simulation theory. If consciousness itself can be simulated, if self-awareness can be coded, then even Descartes' bedrock certainty might rest on silicon rather than soul. We'll return to this question later, but for now, notice how Descartes established the template for radical skepticism about reality. The idea that we might be systematically deceived about everything we think we know. What's remarkable is that these ancient and early modern philosophers, working without any concept of computers or digital technology, all arrived at similar insights. Reality might have layers. What we perceive might be projection rather than fundamental existence. And certainty about the nature of the world is harder to achieve than we initially assume. They were responding to timeless features of human experience. Dreams feel real while we're in them. Illusions can be convincing. Perception is mediated through our senses and interpreted by our brains, introducing multiple opportunities for error or distortion. And consciousness itself remains mysterious. We don't fully understand how subjective experience arises from physical processes, which leaves open the possibility that the relationship between mind and reality is stranger than we think. These philosophers also shared another crucial insight. The question itself matters, regardless of whether we can answer it definitively. Plato's cave allegory wasn't primarily about proving that forms exist. It was about encouraging people to question their assumptions and seek deeper understanding. Zhuangzi's butterfly dream wasn't meant to be solved. It was meant to shake up our certainty and open our minds to mystery. Descartes' demon wasn't really expected to exist. It was a thought experiment designed to establish what we could and couldn't know for certain. In the same way, modern simulation theories' value might lie not in proving we're in a simulation, but in what the question reveals about knowledge, reality, consciousness, and certainty. These ancient thinkers gave us permission to ask radical questions about existence. They established that skepticism about reality isn't madness or mere intellectual game-playing. It's a legitimate philosophical inquiry that can deepen our understanding even when it doesn't provide final answers. Here's something strange about the universe. It does mathematics. Not metaphorically, not approximately, but with perfect precision. An electron doesn't sort of follow quantum equations, it follows them exactly. Planets don't orbit in ways that are kind of like ellipses. Their paths trace perfect conic sections determined by gravitational equations. Light doesn't approximately obey Maxwell's equations. It obeys them to every decimal place we can measure. This is deeply weird when you stop to think about it. Mathematics is something humans invented to describe patterns we observed in nature. Or at least, that's what we thought. But the more physicists have explored the universe, the more it seems like mathematics isn't just our description of reality. It's the source code of reality itself. The universe appears to be running on math. Let's start with a simple example. When you throw a ball, its trajectory follows a parabola, a specific mathematical curve. This isn't just a good approximation. It's exact, determined by equations that were first worked out by people like Galileo and Newton. The ball doesn't think about these equations. It doesn't calculate. It just moves, and its movement can be perfectly described by mathematical formulas. Now you might say that's just because physics is deterministic, cause and effect following natural laws, and that's true. But here's where it gets interesting. Those natural laws are mathematical in nature. They're not just describable by mathematics, they seem to be mathematical in their essence. The relationship between force, mass, and acceleration isn't approximately F equals ma, it is F equals ma. The universe appears to be computing this relationship in real time, perfectly, for every object, everywhere, always. This phenomenon fascinated physicist Eugene Wigner so much that he wrote a famous essay in 1960 titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner pointed out something remarkable. Mathematics developed for purely abstract, theoretical reasons repeatedly turns out to perfectly describe physical reality, often in completely unexpected ways. For example, complex numbers, which involve the square root of -1, something that seems to have no physical meaning, turn out to be essential for quantum mechanics. Group theory, developed by mathematicians studying abstract symmetries, became crucial for understanding particle physics. Riemannian geometry, created to explore curved spaces in pure mathematical speculation, turned out to be exactly what Einstein needed to describe gravity in general relativity. It's as if mathematicians are discovering features of reality by exploring abstract logical relationships, even when they have no idea their work will apply to the physical world. The universe seems to be constructed according to mathematical principles that exist independently of whether anyone knows about them. This is profoundly suggestive for simulation theory. Think about video games. When you play a game, the characters, environments, and physics are all determined by underlying code, mathematical algorithms that define how everything behaves. A simulated ball follows a simulated parabolic arc because the program calculates its trajectory Using the same equations, a real ball would follow. The game world is mathematical because it's computed. Now, what if our universe works the same way? What if the reason mathematics describes reality so perfectly is that reality is mathematics? Not in a metaphorical sense, but literally. What if physical laws are computational rules, and the universe evolves by executing these rules, calculating each moment based on the previous one? This idea becomes even more compelling when we look at quantum mechanics, which is the physics of the very small. Atoms, electrons, photons. Quantum mechanics is unavoidably mathematical in a way that's even more extreme than classical physics. In classical physics, we can describe things in everyday language and then use math to make predictions. But in quantum mechanics, there is no everyday language description that works. The math isn't just useful, it's the only coherent way to talk about quantum reality. An electron doesn't have a definite position and momentum until you measure it. Before measurement, it exists in a superposition, a state described by a mathematical function called a wave function. When you measure the electron, this wave function collapses into a specific outcome, with probabilities determined by the mathematics of quantum theory. But what does it mean for something to exist in superposition? What is the wave function really? These questions don't have clear answers in terms of everyday reality, but the mathematics works perfectly. This has led some physicists and philosophers to suggest that quantum mechanics reveals something fundamental. Reality at its deepest level is information, mathematics, probability. Abstract structures rather than tangible stuff. The particles and forces we observe might be emergent phenomena, arising from more basic mathematical or computational processes. And here's something that really resonates with simulation theory. Quantum mechanics has features that look suspiciously like optimization strategies you'd use in a computer simulation. The uncertainty principle. The fact that you can't simultaneously know both the position and momentum of a particle with perfect precision could be understood as a rendering optimization. If you're simulating a universe and want to save computational resources, you don't need to compute everything in perfect detail all the time. You only need to fully render things when they're being observed. Similarly, quantum entanglement, where particles can be correlated in ways that seem to involve instant communication across space, starts to make more sense if space itself isn't fundamental. In a simulation, two entangled particles might be connected at the level of the underlying code, even if they appear separated in the simulated space. The spooky action at a distance that troubled Einstein might just be a natural consequence of the information structure of reality. Then there's the speed of light. In our universe, nothing can travel faster than light, about 300,000 kilometers per second. This isn't just a practical limit. It's built into the fundamental structure of spacetime itself. But why should there be a maximum speed at all? In a simulation, a maximum processing speed makes perfect sense. Information can only propagate through the simulation at the rate the processor can compute. The speed of light might literally be the universe's refresh rate, the fastest speed at which information can be updated across the simulation. Even more suggestive, spacetime itself appears to be quantized at the smallest scales. The Planck length, about 10 to the power of minus 35 meters, represents the smallest meaningful distance in physics. Below this scale, our current theories break down, and the smooth fabric of spacetime seems to become discrete, pixelated. Similarly, there's a Planck time, about 10 to the power of minus 43 seconds, representing the smallest meaningful interval of time. This is exactly what you'd expect in a simulation. Computer simulations are always discrete, divided into tiny units. Your computer screen shows smooth images, but zoom in enough and you find individual pixels. Time in a computer program flows smoothly from the user's perspective, but it's actually computed in discrete steps. tiny moments when the program updates everything based on the previous state. The Planck scale might be revealing the pixel size and frame rate of our universe. The mathematical nature of physical laws also raises another fascinating point. These laws contain physical constants. Numbers like the speed of light, the gravitational constant, the charge of an electron, that appear to be fine-tuned for life to exist. Change these constants by even a small amount, and atoms wouldn't form, stars wouldn't burn, chemistry wouldn't work, and life would be impossible. There are two ways to interpret this. One is the anthropic principle. We observe these particular constants because if they were different, we wouldn't exist to observe anything. We're selected as observers by the very fact that our universe permits observers. The other interpretation, compatible with simulation theory, is that these constants are parameters, settings chosen by whoever or whatever created the simulation. Just as a video game designer sets various parameters that define how their game world works, a simulation designer might have tuned the physical constants to create a universe capable of developing complex, interesting phenomena. What makes this line of thinking so compelling is that it's not just philosophical speculation. It's grounded in the actual mathematics and physics of our universe. We're not imagining that reality might be mathematical. We're observing that it demonstrably is. The question is what to make of this observation. For centuries, scientists operated under the assumption that mathematics was a human tool for describing a non-mathematical reality. But as physics has progressed, that distinction has become harder to maintain. It increasingly looks like mathematics isn't describing reality. Mathematics is reality, or at least it's the closest we can get to understanding what reality fundamentally is. This creates a strange loop in our understanding. If the universe is mathematical, and mathematics is about information and computation and computation are what computers do, then maybe the universe literally is a computer. Not like a computer, not analogous to a computer, but actually a computational system processing information according to mathematical rules. Of course, this raises new questions. If the universe is computational, what is it running on? What's the hardware? And this brings us back to simulation theory. Maybe our universe is software running on hardware in some higher level of reality. Maybe the mathematical laws we've discovered are the program code, and we're patterns of information within that program. Or maybe mathematics is fundamental in an even deeper way. Maybe there is no hardware, and mathematical structures simply exist in some abstract sense, and our universe is one such structure that happens to include observers who can contemplate their own existence. This is the mathematical universe hypothesis proposed by cosmologist Max Tegmark, which suggests that reality is mathematics, full stop. Either way, whether we're in a simulation running on someone else's computer, or whether we're patterns within a self-existent mathematical structure, the conclusion is similar. The fundamental nature of reality is more abstract, more computational, more information-based than our everyday experience suggests. The solid, tangible world we live in might be an emergent phenomenon, arising from mathematical or computational processes at a more basic level. Picture a hologram, one of those images that appears three-dimensional despite being recorded on a two-dimensional surface. When light hits it just right, a full 3D scene materializes before your eyes. The depth, the volume, the solidity, it's all an illusion, all information encoded on a flat surface. Now imagine something extraordinary. What if our entire universe, with all its vast three-dimensional space, is actually a hologram? What if everything you've ever experienced, every sunrise, every mountain, every moment, is information encoded on a distant two-dimensional surface, projected into the appearance of three-dimensional reality? This isn't science fiction or mystical speculation. This is the holographic principle, one of the most profound ideas to emerge from theoretical physics in the last 50 years. And it suggests that the universe might be even stranger than simulation theory proposes. Not just virtual, but fundamentally informational in nature, with one less dimension than it appears to have. The story begins, oddly enough, with black holes. In the 1970s, physicist Stephen Hawking made a disturbing discovery. Black holes aren't completely black. They emit radiation, now called Hawking radiation, and they slowly evaporate over time. This created a serious problem for physics because it seemed to violate a fundamental principle: information cannot be destroyed. Here's the issue: when anything falls into a black hole, it takes its information with it. The quantum state of every particle, every detail about its configuration and history. If the black hole then evaporates completely, radiating away its mass as random Hawking radiation, that information seems to disappear from the universe forever. But quantum mechanics says this can't happen. Information has to be conserved. It can be scrambled, transformed, made difficult to access, but never truly destroyed. This paradox, the black hole information paradox, troubled physicists for decades. And the solution, proposed by Leonard Susskind and Gerard T. Hooft in the 1990s, was radical. Maybe the information doesn't fall into the black hole at all. Maybe it's encoded on the black hole's surface. The event horizon, the boundary beyond which nothing can escape. As matter approaches and crosses the event horizon, its information gets smeared across this two-dimensional surface like a hologram. But here's where it gets really interesting. They realized this principle might not just apply to black holes, it might apply to the entire universe. Maybe all the information about everything in our three-dimensional space is actually encoded on a two-dimensional boundary at the edge of the universe. The depth, the volume, the three-dimensionality we experience. It might all be a projection, a hologram, arising from information fundamentally stored in one fewer dimension. Think about this carefully because it's genuinely mind-bending. You are, right now, experiencing yourself as a three-dimensional being in three-dimensional space. You can move forward, backward, left, right, up, down. You occupy volume. But according to the holographic principle, you might actually be information encoded on a distant two-dimensional surface. And your three-dimensional experience is something like a hologram projected from that surface. This isn't just wild speculation. The holographic principle has become a serious research program in theoretical physics, with mathematical support from string theory and other frameworks. It addresses real problems in quantum gravity and provides new ways of thinking about the relationship between quantum mechanics, gravity, and information. The principle suggests something profound about the nature of space itself. We usually think of space as fundamental, a container that exists independently, and then matter and energy occupy positions within it. But the holographic principle suggests that space might be emergent, arising from more fundamental information-theoretic structures. The three-dimensional universe we inhabit might be a kind of illusion, or at least a derived phenomenon, with the real action happening in fewer dimensions. This connects deeply with simulation theory. If our universe is a simulation, the simulation doesn't necessarily run in the same dimensionality as what it displays. A video game can show a convincing 3D world while running on hardware that processes information in fundamentally different ways. The graphical processing unit in your computer doesn't contain three-dimensional space. It contains transistors processing information, and that information is used to generate images that create the illusion of three-dimensional space on your screen. Similarly, if we're in a simulation that's holographic in nature, the simulation might be running on a two-dimensional substrate, with three-dimensional space being something that emerges from how information is organized and processed. You wouldn't need a three-dimensional computer to simulate a three-dimensional universe. You just need enough information processing capacity on a two-dimensional surface. There's another aspect of the holographic principle that resonates with simulation theory: the relationship between information and area. In our everyday experience, the amount of information an object can contain should be related to its volume. Bigger objects should be able to store more information, but the holographic principle says that's wrong. The maximum information is related to the object's surface area, not its volume. This is counterintuitive, but it makes perfect sense in a simulation. If you're rendering a 3D environment, you don't need to compute the entire interior of every object in perfect detail. You only need to compute what's visible, the surface. The interior can be computed as needed or represented more efficiently. This is exactly how computer graphics work. Clever algorithms determine what's visible and render only that, saving computational resources. The fact that information in our universe seems to work the same way, bounded by surface area rather than volume, suggests that our reality might be more concerned with what's observable, what's at boundaries and surfaces, than with internal details. This is precisely what you'd expect in a simulated or computed reality, where efficiency matters. The holographic principle also provides a new perspective on the measurement problem in quantum mechanics. The fact that quantum systems exist in superposition until they're measured, at which point they collapse into definite states. If information is fundamentally holographic, stored on boundaries rather than in volumes, then measurement might be the process by which three-dimensional phenomena emerge from two-dimensional information. The act of observation might literally be the process that projects the hologram, bringing definite reality into existence from quantum possibility. Physicist Juan Maldacena developed an influential example of holographic principles called the ad-SCFT correspondence. This mathematical framework describes how a theory of gravity in a space with certain properties, called anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity on the boundary of that space, a space with one fewer dimension. Everything happening in the higher dimensional gravitational theory can be completely described by a lower dimensional theory without gravity. What makes this remarkable is that it's a precise mathematical equivalence, not just an analogy. The two theories are different ways of describing the exact same physical situation. One description involves gravity, curved spacetime, and extra dimensions. The other involves quantum fields, flat space, and fewer dimensions. They're completely equivalent, like two languages describing the same reality. This suggests something profound. Dimensions might be more flexible than we think. What we experience as the dimensionality of space might be a matter of perspective, of which description we're using, rather than a fundamental feature of reality. You could describe our universe using different numbers of dimensions depending on your mathematical framework, and each description would be equally valid. For simulation theory, this is significant because it means the question, how many dimensions does reality have, might not have a single answer. The reality that's being simulated might have a different dimensionality than what's experienced by beings within the simulation. We might be information patterns in a lower dimensional substrate that's being processed in ways that generate the experience of three-dimensional space. There's also a connection here to information theory more broadly. Information has become increasingly central to physics over the past few decades. Physicists have realized that many fundamental questions are really questions about information. What information can be extracted from a system? How is information encoded and transformed? What are the limits on information processing imposed by physical law? The holographic principle takes this information theoretic perspective to its logical extreme. Maybe information isn't just important for understanding physics. Maybe information is what physics fundamentally describes. Maybe the universe isn't primarily made of matter and energy, with information as a secondary property. Maybe information is primary, and matter and energy are patterns within information. This is remarkably close to saying the universe is a computation, because computation is fundamentally about information processing. If reality is information, structured and organized according to mathematical rules, transforming from moment to moment in lawful ways, then reality is computational. Whether or not someone designed it, whether or not it's running on external hardware, it's still computational in its essential nature. As you settle into sleep, imagine yourself dissolving into information, not in a scary way, but peacefully, naturally. Your body is really just information, quantum states of particles, all describable mathematically. Your thoughts are information patterns in neural networks. Your memories are information encoded in synaptic connections. Even your sense of being a continuous self over time is information, a narrative your brain constructs from discrete moments. In this view, you were always information. The holographic principle just makes explicit what was always true. You're not a solid thing in solid space. You're a pattern of information, temporarily organized in ways that create the experience of being a person in a world. That pattern might be encoded on surfaces, projected into dimensions, computed from mathematical structures. But it's always been information all along. And information, unlike matter, isn't localized in the same way. It can be copied, transferred, encoded in multiple substrates. If you're fundamentally information rather than stuff, then the question of whether you're really real or just simulated loses some of its force. Information is information, regardless of the medium. The pattern that is you, the organized complexity that thinks and feels and dreams, would be just as real whether encoded in atoms or bits, in 3 dimensions or 2, in base reality or simulation. In 2003, a philosopher at Oxford University published a paper that would become one of the most discussed arguments in contemporary philosophy. Nick Bostrom's "Are You Living in a Computer Simulation?" didn't just speculate about the possibility that we might be in a simulation. It presented a logical argument suggesting that at least one of 3 possibilities must be true, and that one of those possibilities is that we almost certainly are living in a simulation. The paper is only 14 pages long, but it sparked thousands of academic articles, countless podcast discussions, and became a favorite topic of conversation among Silicon Valley technologists and philosophers alike. What makes Bostrom's argument so compelling isn't mysticism or sci-fi speculation. It's cold logic, probability, and extrapolation from current technological trends. Let's walk through the argument carefully, because it's elegant in its simplicity even as it's profound in its implications. Bostrom starts with an observation about the future of computing. If technological civilization continues advancing at anything like its current pace, future civilizations will have access to computational power that dwarfs anything we can currently imagine. Moore's law, the observation that computing power roughly doubles every 2 years, may not continue forever, but even conservative estimates suggest computers in a few hundred or 1,000 years could be trillions of times more powerful than today's machines. With that kind of computational power, a future civilization could run extremely detailed simulations of their ancestors, people like us, living in simulated worlds that would be indistinguishable from reality to the simulated inhabitants. These wouldn't be simple video game characters following basic scripts. They'd be fully conscious beings, or at least beings who believed themselves to be conscious, with rich internal lives, memories, relationships, and experiences. Now here's where probability comes in. If it becomes possible to run such simulations, and if civilizations choose to run them, they could run not just one simulation, but millions or billions. After all, once you have the capability and the simulation software, running additional simulations costs relatively little. Maybe different civilizations run simulations to study their history, to explore counterfactual scenarios, to entertain themselves, or for reasons we can't imagine. Think about the numbers in base reality, the fundamental, non-simulated universe. there might be thousands or millions of advanced civilizations. But each of those civilizations might run billions of ancestor simulations. So there would be billions of simulated realities for every one base reality. This means that the vast majority of beings who think they're living in the early 21st century would actually be in simulations. If there are a billion simulated worlds and one base reality, and you find yourself apparently in the early 21st century, the odds are about 1,000,000,000 to 1 that you're in a simulation rather than base reality. But Bostrom acknowledges that this conclusion only follows if certain conditions are met. This is where his famous trilemma comes in. At least one of the following 3 propositions must be true. First, almost all civilizations at our current level of development go extinct before reaching the capability to run ancestor simulations. Maybe nuclear war destroys us. Maybe climate change makes Earth uninhabitable. Maybe there's some unknown filter ahead that prevents civilizations from reaching the technological maturity necessary to run such simulations. If this is true, we don't need to worry about whether we're in a simulation, because there won't be anyone around to run them. But it does mean humanity's future is rather grim. Second, the fraction of civilizations that reach technological maturity and then choose to run ancestor simulations is very close to 0. Maybe advanced civilizations lose interest in simulating their ancestors. Maybe it's considered unethical. Simulating conscious beings who don't know they're simulated could be seen as a form of imprisonment or deception. Maybe advanced civilizations focus their computational resources on other projects they find more valuable. If this is true, then even though simulations become possible, they don't actually get run in significant numbers, so we're probably not in one. Third, we are almost certainly living in a computer simulation. If civilizations don't generally go extinct before reaching simulation capability, and if at least some of them do run ancestor simulations, then the statistical argument kicks in. The simulated beings would vastly outnumber beings in base reality. So we should assume we're probably among the simulated rather than the rare base reality inhabitants. This is Bostrom's trilemma. We can't know which of these 3 options is true, but at least one must be. Either we're doomed, or simulations don't get run, or we're almost certainly in one. Those are the logical possibilities. What makes this argument so unsettling is that it doesn't rely on exotic physics or controversial assumptions. It's based on straightforward reasoning about computational capacity, probability, and technological trends. You don't need to believe anything particularly strange to accept the logic. You just need to accept that computing power continues advancing, and that simulating consciousness is possible in principle. That second assumption, that consciousness can be simulated, deserves closer examination. Bostrom assumes what philosophers call substrate independence of consciousness. This is the idea that consciousness doesn't depend on being implemented in biological neurons specifically, but could arise from any sufficiently complex information processing system organized in the right way. If substrate independence is true, then a perfect simulation of a brain would be conscious in the same way a biological brain is conscious. The simulated person would have real experiences, real thoughts, real feelings. They just wouldn't know they were simulated. Their reality would be computed rather than fundamental, but from their perspective, it would be completely real. This assumption is controversial, but increasingly accepted among neuroscientists and philosophers of mind. After all, there doesn't seem to be anything magical about biological neurons. They're complex, but they're ultimately just physical systems following natural laws. If we can understand those laws completely and simulate them accurately, why wouldn't the simulation be conscious? Some people object that consciousness requires something special. Perhaps quantum effects in microtubules, perhaps some non-physical soul or spirit. But most neuroscientists working on consciousness believe it emerges from the brain's information processing in ways that could, in principle, be replicated computationally. If they're right, then substrate independence follows, and Bostrom's argument stands. Another interesting aspect of Bostrom's argument is what it implies about the purpose of simulations. If we're in an ancestor simulation, we're probably being simulated by our own descendants, or at least by beings descended from civilizations similar to ours. They might be running these simulations to understand their history, to explore how things might have developed differently, or perhaps to preserve their past in some form. This raises ethical questions that Bostrom explores in later work. If you're running a simulation populated by conscious beings, what responsibility do you have to them? Is it ethical to create beings who believe they're in base reality when they're not? What if the simulation experiences suffering? Should you intervene when simulated beings face disasters, or let the simulation run its course? These questions might seem abstract, but they could become very practical very soon. As our own computing power increases, we might develop the capability to run simulations sophisticated enough to raise questions about whether simulated entities deserve moral consideration. We might find ourselves in the position of the simulators, forced to confront these ethical dilemmas directly. Some philosophers and technologists have taken Bostrom's argument very seriously. Elon Musk has said he believes the odds we're in base reality are 1 in billions. Philosopher David Chalmers has written extensively about the philosophical implications if we are in a simulation, arguing that simulated reality would still be genuinely real to its inhabitants. Physicists have proposed experiments that might detect evidence of simulation, looking for computational artifacts or limitations. But Bostrom himself is careful to note that his argument doesn't prove we're in a simulation. It proves that at least one of 3 things is true, and we don't know which. We might indeed be in a simulation, but we might also be heading for extinction. Or we might live in a universe where advanced civilizations simply don't run ancestor simulations. There's also a 4th logical possibility that Bostrom acknowledges. We might be wrong about the feasibility of conscious simulations. If consciousness can't be substrate independent, if there's something special about biological implementation that can't be captured in simulation, then the whole argument doesn't get off the ground. Simulations might be possible but not conscious, in which case there's no meaningful sense in which we could be in one. The argument also assumes that simulated beings would be convincingly real, that the simulation would be detailed enough that inhabitants couldn't easily tell they were simulated. If simulations were obviously simulated, full of glitches, limitations, or inconsistencies, then we could be fairly confident we're not in one, since our reality seems consistent and lawful. But if technology advances far enough, creating convincing simulations might be well within capability. As you drift toward sleep, consider the strange loop Bostrom's argument creates. If the argument convinces many people that we're probably in a simulation, and if those people then decide not to run simulations of their own ancestors, perhaps for ethical reasons, that would make option 2 true. Civilizations don't run simulations, but that would make option 3 false. We're probably not in a simulation. The act of believing the argument and acting on it would make the argument's conclusion false. Unless, of course, our choices don't matter because we're already in a simulation, and our simulated choices can't affect whether base reality civilizations run simulations, or unless this very consideration is why some civilizations in base reality choose not to run simulations. They realize the ethical implications and decide against it. The logic spirals recursively, simulations potentially nested within simulations, each level uncertain about whether there's another level above. What Bostrom achieved with his paper was making simulation theory respectable in academic philosophy and science. Before his argument, Simulation theory was mostly the domain of science fiction and fringe speculation. After his paper, it became a serious topic for scholarly discussion, analyzed in peer-reviewed journals, debated at academic conferences. Whether or not we're actually in a simulation, Bostrom showed that the question deserves serious consideration. It's not crazy to wonder about it. It's not unscientific to explore it. Given certain plausible assumptions about computation, consciousness, and technological development, simulation theory becomes not just possible, but probable. And that's perhaps the most unsettling thing about Bostrom's argument. It doesn't require you to believe anything outlandish. It just asks you to extrapolate current trends, accept some reasonable philosophical positions, and follow the logic. And the logic leads, inescapably, to the trilemma: extinction, choice, or simulation. One of these must be true, we just don't know which. You're driving down a familiar road when you see the same car, the same make and model, the same color, pass you twice in impossible succession. Or you walk into a room and experience the uncanny certainty that this exact moment has happened before. Déjà vu so strong it's almost overwhelming. Or you clearly remember a book title or movie line one way, only to discover that everyone else remembers it differently, and when you check, your memory is wrong. These moments feel like glitches, brief flickers where reality seems to stutter or reveal its seams. If we're in a simulation, we might expect to occasionally observe anomalies. Places where the simulation's limitations become apparent, moments when the processing power isn't quite sufficient, or instances where the code produces unexpected results. Some proponents of simulation theory have pointed to various strange phenomena in our universe as potential evidence of such glitches. Let's explore these claimed anomalies with both openness and healthy skepticism. The measurement problem in quantum mechanics might be the most profound strangeness in all of physics. Quantum systems exist in superposition, multiple states simultaneously, until they're measured. An electron can be in multiple places at once, spinning both clockwise and counterclockwise, until you observe it, at which point it chooses a definite state. The act of observation appears to affect reality at the most fundamental level. This has puzzled physicists since quantum mechanics was developed. How does the universe know when something is being observed? What counts as a measurement? Why should observation have any special role in physics? Various interpretations have been proposed. The Copenhagen interpretation, many worlds, pilot wave theory. But none fully resolves the weirdness. But if we're in a simulation, the measurement problem makes perfect sense. It's a rendering optimization. Think about how computer graphics work. A sophisticated game doesn't compute every detail of its entire world every moment. Instead, it uses level of detail systems. Distant objects are rendered in less detail. Things outside your field of view might not be rendered at all, and fine details only get computed when the camera gets close enough that you'd notice them. Similarly, a universe simulation might not need to compute the exact state of every particle all the time. Most particles never interact with observers and never have their precise states measured. Why waste computational resources calculating details that will never be observed? Instead, the simulation could keep particles in superposition, represented probabilistically, requiring minimal computation, and only collapse them into definite states when observation occurs, when the information becomes relevant. This would explain why particles behave like waves, probabilistic, spread out, indefinite when unobserved, but like particles, definite, localized when measured. The wave is the low-resolution, computationally efficient representation. The particle is the high-resolution render that gets computed only when necessary. Of course, this interpretation isn't proven, but it's intriguing that quantum mechanics exhibits exactly the behavior you'd expect if reality were being computed with intelligent optimization strategies to save processing power. Quantum entanglement presents another strangeness that simulation theory might explain. When particles become entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, because it seems to violate the principle that nothing can travel faster than light. How can measuring a particle here instantly affect a particle light years away? In our normal understanding of space, this is deeply mysterious. But in a simulation, space isn't fundamental. It's part of the simulated environment. At the level of the underlying code, two entangled particles might be connected by data structures that have nothing to do with simulated distance. They're like two variables in a program that reference the same memory location. Change one, and you've changed what the other references to instantly, because there's no actual distance between them at the code level. The simulation doesn't need to send information across space at faster-than-light speeds. The information never travels through simulated space at all. It's updated in the underlying computational substrate where spatial distance is irrelevant. This would explain why entanglement doesn't actually allow faster-than-light communication. You can't control what state your particle collapses to, so you can't send messages, even though it creates instantaneous correlations. The speed of light itself is suggestive. Why should the universe have a maximum speed? It's not obvious from first principles that there needs to be a cosmic speed limit. But in a simulation, a maximum information propagation speed makes perfect sense. It's the rate at which the simulation can update. The processor has a maximum speed at which it can compute state changes, and that manifests in the simulated universe as a maximum speed at which anything can happen or any information can travel. The fact that the speed of light is the same for all observers, regardless of their motion, one of the key insights of special relativity, also makes more sense in simulation terms. If space and time are both emergent properties of how the simulation processes information, then the rate of information propagation would naturally be constant across the simulation, independent of any observer's state of motion within the simulated environment. Then there's the fine-tuning problem. The physical constants of our universe, the strength of gravity, the electromagnetic force, the mass of fundamental particles, appear to be exquisitely fine-tuned for life to be possible. Change these constants by even tiny amounts, and atoms wouldn't form. Stars wouldn't shine, chemistry wouldn't work, and life couldn't exist. There are roughly 3 ways to explain this. One is pure chance. We got lucky, but the odds seem astronomically against this. Another is the anthropic principle. We observe these particular constants because if they were different, we wouldn't exist to observe anything. This is logically true, but feels somewhat unsatisfying. The third explanation is design. Someone or something set these constants to values that would produce an interesting, life-bearing universe. Simulation theory provides a version of this design explanation. The constants are parameters, settings chosen when the simulation was initialized. Maybe they were chosen specifically to create a universe capable of developing complex life and consciousness. Or maybe our simulators ran many simulations with different parameters, and we happened to be in one of the ones that worked. Either way, fine-tuning makes sense if the universe is a created simulation rather than a brute fact. The Planck scale, the smallest meaningful distance in time in physics, looks suspiciously like pixelation. Below the Planck length, our physics equations break down. Space and time stop being smooth and continuous and start becoming discrete, quantized. This is exactly what you'd expect at the bottom of a simulation, where you'd eventually hit the resolution limit. The size of the pixels, or the length of the time, steps in which the simulation updates. Some physicists researching loop quantum gravity and other approaches to quantum gravity suggest that spacetime itself might be fundamentally discrete, made of tiny loops or units rather than being infinitely divisible. This would mean the universe is, at its deepest level, more like a cellular automaton or a vast computational grid than like a smooth fabric. Reality would be digital, not analog. Now let's talk about déjà vu and the Mandela effect, phenomena that some people suggest might be simulation glitches. Déjà vu, the feeling that you've experienced something before even though you know you haven't, is remarkably common. Most people experience it occasionally. Neuroscience has some explanations involving memory systems misfiring or brief delays in how the brain processes information, but the experience remains eerie. If we're in a simulation, déjà vu might occur when the simulation slightly lags or repeats. Maybe you briefly experience the same rendered moment twice because of a processing hiccup. Or maybe your simulated memory is accidentally updated with information from a moment you haven't technically experienced yet. These are just speculations, of course. Neuroscientific explanations are far more likely to be correct. The Mandela effect refers to situations where large groups of people share false memories, remembering things differently from how they actually are. The name comes from many people remembering that Nelson Mandela died in prison in the 1980s, when he actually lived until 2013. Similarly, many people remember the Berenstain Bears children's books being spelled Berenstein, or remember a movie called Shazam, starring comedian Sinbad, that apparently never existed. Some enthusiasts suggest these shared false memories are evidence of simulation updates. That reality was edited, perhaps to fix a bug or change something, and most memories were updated, but some people retained memories from the previous version. More prosaically, psychologists explain the Mandela effect through normal cognitive biases, false memory formation, and the way human brains reconstruct rather than replay memories. The simulation explanation is creative but almost certainly wrong. Human memory is notoriously unreliable, and shared false memories can emerge from common sources of misinformation or similar cognitive biases affecting many people. But the phenomenon does illustrate how people experiencing simulation theory start reinterpreting ordinary experiences as potential evidence. There are also claimed anomalies in large-scale cosmic structures. Some researchers have pointed to certain patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, as potentially too regular to be natural. Others have noted that galaxies seem to be distributed in ways that might suggest underlying computational grids. These claims are controversial and not accepted by mainstream cosmology, but they represent attempts to find evidence of simulation in astronomical data. One proposed test for simulation theory involves looking for computational artifacts. If the universe is simulated on a cubic lattice, for instance, there might be directional preferences in how ultra-high-energy cosmic rays arrive at Earth. They might preferentially align with lattice directions. So far, experiments haven't found such evidence, but the search continues. Of course, we should be careful about confirmation bias here. If you're looking for glitches, you'll find them everywhere. The human brain is excellent at finding patterns, sometimes too excellent. We see faces in clouds, meaning in coincidences, and conspiracy in randomness. Many claimed glitches in the matrix are probably just this pattern-seeking tendency applied to ordinary phenomena. But some of the strangeness in physics genuinely does align with what you might expect from a simulation. Quantum mechanics behaves like a rendering optimization. Entanglement looks like it exploits information structure beneath apparent space. The speed of light acts like a processing speed limit. Constants seem fine-tuned like parameters. Space seems pixelated at small scales. None of this proves simulation theory. Each phenomenon has other explanations, often well-developed scientific explanations that don't require assuming we're in a computer program. But the accumulation of strange features that happen to be exactly what you'd expect in a sophisticated simulation is at minimum interesting and at maximum suggestive. Let's talk about something practical. If we wanted to simulate a universe like ours, could we actually do it? Not in the abstract, but with real computing hardware, real energy requirements, real physical constraints. This is where simulation theory moves from philosophy to engineering, where we have to confront the sheer scale of what would be required to compute reality. Start with something simple, a cup of coffee. That coffee contains roughly 10 to the power of 25 molecules. That's 10 trillion molecules. Each molecule is made of atoms, each atom of subatomic particles, each of those following quantum mechanical laws that require enormous amounts of information to describe. To simulate that cup of coffee at the quantum level, tracking the state of every particle and computing all their interactions, would require computational power that vastly exceeds everything humanity has ever built. Now scale up to a room, a city, a planet, a solar system, a galaxy, a universe. The amount of computation required becomes so large it's hard to even conceptualize. Our observable universe contains roughly 10 to the power of 80 atoms. If you wanted to simulate each of those at the quantum level, you'd need to track an almost incomprehensible amount of information. Let's put some numbers to this. A human brain contains about 86 billion neurons, each with thousands of synapses, creating roughly 100 trillion connections. Simulating a single human brain in real time, at the level of individual neurons and synapses, requires computational power we're only beginning to approach. The whole brain simulation, projects currently underway need supercomputers, running for hours or days, to simulate seconds of brain activity. But that's just one brain at the classical level. To simulate a brain at the quantum level, you'd need to track the quantum states of every molecule involved in neural signaling. Neurotransmitters, ion channels, membrane proteins. The computational requirements multiply exponentially. Some neuroscientists argue you don't need quantum-level simulation for consciousness. Classical neural networks might be sufficient, but we don't know that for certain. Now multiply one brain by 8 billion current humans, plus all the humans who have ever lived if we're in an ancestor simulation, plus all the non-human life that's ever existed, plus all the geological processes, weather systems, and astronomical phenomena. The computational requirements are staggering. But here's where the argument gets interesting. Bostrom's simulation hypothesis assumes we're talking about civilizations far more advanced than ours. If computing power continues advancing at anything like current rates, even accounting for the inevitable slowdown as we approach physical limits, future civilizations could have access to computational resources that make our current capabilities look like abacuses. Consider Moore's law, the observation that the number of transistors in integrated circuits doubles approximately every 2 years. This doubling has held remarkably consistent since the 1960s. If it continues for even a few more decades, we'll have computers millions of times more powerful than today's. Extend it a few centuries, and the numbers become astronomical. Of course, Moore's law can't continue forever. There are physical limits. Eventually you hit the atomic scale, quantum effects interfere, heat dissipation becomes impossible. But even if transistor density plateaus, there are other avenues for computational advancement. Quantum computing, photonic computing, neuromorphic architectures, molecular computing. Quantum computers deserve special attention here. Traditional computers process information in bits that are either 0 or 1. Quantum computers use qubits that can be in superposition, both 0 and 1 simultaneously. This allows quantum computers to perform certain calculations exponentially faster than classical computers. A quantum computer with just a few hundred qubits could, in principle, perform calculations that would take a classical computer longer than the age of the universe. Here's the really interesting part. Quantum computers might be ideal for simulating quantum systems. Physicist Richard Feynman originally proposed quantum computers for exactly this purpose. to simulate quantum mechanics efficiently. It takes exponentially growing classical computing resources to simulate quantum systems, but a quantum computer could simulate them with resources that scale linearly. If the universe is quantum mechanical, which it is, then quantum computers might be able to simulate it far more efficiently than we'd think based on classical computing alone. But there's a clever workaround that makes simulating a universe much more feasible. You don't have to simulate everything in full detail all the time. Remember the rendering optimization we discussed with quantum mechanics. The same principle applies to simulation more broadly. Think about how video games work. A modern game might present a vast open world with cities, landscapes, weather, and thousands of characters. But the game doesn't actually compute all of that simultaneously. It renders what's on your screen in high detail, keeps nearby areas in medium detail ready to load quickly, and represents distant areas as low-resolution data, or doesn't compute them at all until needed. As you move through the game world, it dynamically shifts what's being fully simulated. A universe simulation could work similarly. You don't need to compute the interior of every star in full detail. You only need to compute what's being observed or what affects observable things. You don't need to track every particle in interstellar space. You can represent vast empty regions with statistical approximations. You only need full quantum-level detail for things that are being directly measured or that affect measurements. This is the principle behind quantum mechanics measurement problem viewed through simulation lens. Particles exist in superposition, low-detail, probabilistic representation, until measured, at which point they collapse into definite states, high-detail, specific representation. The simulation renders only what's necessary. With rendering optimization, the computational requirements for simulating a universe drop dramatically. You're not simulating 10 to the power of 80 atoms in full detail. You're simulating a much smaller set of actually observed phenomena in detail, with everything else represented efficiently. The universe becomes computable. There's another consideration: time. A simulation doesn't need to run in real time relative to the base reality. If a simulation is running slowly, say 1 simulated second requires a year of base reality computation, the simulated beings would never notice. Their consciousness, their perception of time passing, is all internal to the simulation. The simulation could be running on a computer that takes millions of years to simulate one human lifetime, and the simulated people would experience that lifetime as normal. This means even if we can't currently imagine computers powerful enough to simulate a universe in anything approaching real time, it doesn't matter. Given enough time and enough computational resources that an advanced civilization might have, you could simulate incredibly complex systems. What about energy? Computing requires energy, and thermodynamics sets fundamental limits on energy-efficient computation. There's a theoretical minimum energy required to perform a computation, related to the entropy change involved, established by Landor's principle. But even those fundamental limits leave enormous room for improvement over current technology. An advanced civilization might have access to energy sources we can barely imagine. Fusion power, matter-antimatter annihilation, extracting energy from black holes, tapping into vacuum energy, or harvesting the entire output of stars using Dyson spheres. With sufficient energy and advanced enough technology, even very computationally expensive simulations become possible. The Kardashev scale classifies civilizations by their energy usage. A Type I civilization can use all the energy available on its planet. Type II can harness all the energy from its star. Type III can use the energy of its entire galaxy. We're currently around 0.7 on this scale. A Type II civilization, with access to the total energy output of a star, would have computational resources that make our current capabilities look infinitesimal. Some researchers have proposed that advanced civilizations might use black holes for computation. The event horizon of a black hole represents maximum information density. The holographic principle again. And rotating black holes could theoretically be used as incredibly efficient computers. These are speculative ideas, but they suggest that fundamental physics might allow for computing capabilities far beyond what we can currently achieve. There's also the question of substrate. What are you actually computing on? Current computers use silicon transistors, but that's not the only option. Molecular computers could use individual molecules as computational elements. Quantum computers use quantum systems. Some physicists have proposed using the very fabric of spacetime itself for computation, effectively turning portions of the universe into computational substrate. If consciousness is substrate independent, if what matters is the pattern of information processing rather than what's doing the processing, then you could implement minds in almost any physical system organized appropriately. You could run consciousness on silicon, on photonic systems, on quantum fields, on exotic matter configurations we haven't discovered yet. This raises a strange possibility. Maybe the simulation isn't running on anything we'd recognize as a computer. Maybe it's implemented in ways that use physics totally unlike our own. The base reality might have entirely different physical laws, different dimensions, different fundamental particles. The simulation could be a translation layer, converting the native physics of base reality into the physics we experience. Or here's an even stranger thought. Maybe there's no clear distinction between the simulation and the hardware it runs on. In our universe, we're used to software being distinct from hardware. Programs run on computers, but you can move the program to different computers. But what if the universe is a kind of computation where the laws of physics are the program, and the substrate is just whatever mathematical or information theoretic structure instantiates those laws? The hardware might be abstract mathematical existence itself. This connects back to the mathematical universe hypothesis we discussed earlier. Maybe all mathematically consistent structures exist in some abstract sense, and consciousness arises in those structures complex enough to support it. We'd be in a simulation, not in the sense of running on someone's computer, but in the sense of being patterns within a mathematical structure. Walk into a tech company in Silicon Valley, strike up a conversation in the cafeteria, and there's a reasonable chance someone will tell you they think we're probably living in a simulation. It's become something of a cultural phenomenon in certain circles, particularly among technologists, entrepreneurs, and people working at the cutting edge of computing and artificial intelligence. The question is, why has simulation theory resonated so powerfully in contemporary culture? The Matrix, released in 1999, didn't invent simulation theory, but it brought the idea into mainstream consciousness with unprecedented impact. The film's premise, that humanity lives in a simulated reality while their actual bodies are used as batteries by AI overlords, became a cultural touchstone. Red pill and blue pill entered the language as metaphors for choosing uncomfortable truth versus comfortable illusion. The image of reality as green cascading code became iconic. The film arrived at a perfect cultural moment. Y2K anxiety had people worried about computer systems failing. The internet was transforming from niche technology to mass phenomenon. Virtual reality and immersive gaming were advancing rapidly. People were beginning to spend significant time in digital environments. Early social media, online games, virtual communities. The boundary between real and virtual life was blurring. The Matrix gave form to nascent anxieties about technology, reality, and control. It suggested that our increasing dependence on digital systems might reflect a deeper truth, that we'd always been dependent on systems we didn't understand or control. The film was paranoid and liberating simultaneously, paranoid in suggesting reality might be false, liberating in suggesting we might escape to something more authentic. But here's what's interesting. The film treats simulation as dystopian, something to escape from, to fight against. The heroes leave the matrix for the desert of the real, choosing harsh truth over pleasant fiction. Yet in real life, many people who believe in simulation theory don't find it distressing. They find it fascinating, even exciting. Why? Part of the answer lies in the specific community that's embraced the idea most enthusiastically: Silicon Valley technologists. These are people who build virtual worlds professionally, who create simulations and games and digital experiences. To them, the idea that reality itself might be a simulation isn't terrifying. It's almost flattering. It suggests that what they do, creating virtual realities, is fundamentally important, perhaps reality adjacent rather than merely entertaining. Elon Musk has become simulation theory's most famous contemporary advocate. In a 2016 interview, he argued there's only a 1 in billions chance we're in base reality. His reasoning follows Bostrom's logic. Given the pace of improvement in video games and virtual reality, he expects that eventually simulations will become indistinguishable from reality. Once that happens, there will be vastly more simulated realities than base reality, so we should assume we're in one of the simulations. Musk's embrace of the idea has helped normalize it in tech culture. When one of the world's richest and most influential technologists casually mentions living in a simulation, it stops being fringe speculation and becomes acceptable dinner party conversation. Other tech leaders, Palmer Luckey, founder of Oculus VR, Rizwan Virk, video game entrepreneur, have similarly engaged with simulation theory publicly. This raises interesting questions about motivated reasoning. Are technologists drawn to simulation theory because the evidence supports it, or because it flatters their worldview, casting their work creating virtual realities as cosmically significant? Is there confirmation bias at play, where people who spend their days programming see programming everywhere, including in the fundamental structure of reality? Philosopher David Chalmers has written extensively about the philosophical implications of simulation theory from a different angle. Chalmers argues that even if we are in a simulation, the simulation is genuinely real. Our experiences are real experiences, our relationships are real relationships, our lives are real lives. The simulated objects we interact with are real objects, they're just made of bits rather than atoms. This challenges the assumption that simulated means fake or less real. In Chalmers' view, reality isn't about what substrate things are implemented on. It's about structure, pattern, and relationship. A simulated tree is a real tree. It just happens to be made of information rather than cellulose. Your simulated body is your real body. Your simulated consciousness is your real consciousness. This philosophical stance diffuses much of the existential anxiety simulation theory might provoke. If the simulation is real, then discovering you're in one doesn't change anything fundamental about your life or its meaning. You're still you, your experiences still matter, your choices still have consequences. You're just implemented in software rather than wetware. So what? But not everyone finds this comforting. Some people experience genuine distress thinking about simulation theory, feeling it threatens the meaning and authenticity of their lives. If we're all NPCs in someone's game, doesn't that make everything arbitrary? If the simulation could be paused, altered, or shut down, how can anything matter? These concerns reflect deeper anxieties about meaning, control, and authenticity that simulation theory crystallizes but doesn't create. The fear that life might be meaningless, that we might lack real agency, that powerful forces beyond our understanding control our fate. These are ancient human fears. Simulation theory just gives them a modern technological form. Religious and spiritual communities have also engaged with simulation theory, finding interesting resonances with traditional beliefs. Some Christian theologians note similarities between simulation theory and classical theism. Both posit a creator outside the system who sustains it. Both suggest our reality depends on something beyond itself. Buddhist thinkers connect simulation theory to concepts of Maya and emptiness, the idea that conventional reality is illusory or lacks inherent existence. Hindu philosophy's simulation-like concepts, the universe as divine dream or play, Leela, have been cited as ancient versions of simulation theory. Some New Age thinkers embrace simulation theory as validation of spiritual teachings about consciousness creating reality. The Gnostic idea of material reality as a flawed copy of a higher realm resonates with some versions of simulation theory. This spiritual engagement with simulation theory is fascinating because it shows how an idea emerging from computer science and probability theory can connect with age-old religious intuitions. The specific metaphors differ: cosmic consciousness versus cosmic computer. But the basic structure is similar. This reality depends on and derives from something more fundamental. There's also been artistic engagement with simulation theory beyond the Matrix. Films like Inception, Westworld, and Black Mirror explore variations on simulated reality, nested realities, and the blurring of real and virtual. These works explore the emotional and philosophical implications. What if your memories were programmed? What if the people you love are NPCs? What if you're a simulation of a real person rather than an original consciousness? Rick and Morty has repeatedly played with simulation concepts, including an episode where characters debate whether they're in a simulation while simultaneously simulating their own characters in a video game, creating recursive layers of simulation while satirizing the entire concept. This self-aware, slightly ironic engagement with simulation theory reflects a generation comfortable with virtual environments and digital identity. Video games themselves have become increasingly philosophical about their own nature. Games like the Stanley Parable, The Beginner's Guide, and Nier Automata explicitly explore what it means to be a character in a game, whether NPCs could be conscious, and whether freedom means anything in a deterministic, programmed environment. Players navigate these games aware they're in simulations, while the games question whether players themselves might be similarly constrained. Social media has created interesting simulation-like dynamics even without literal simulation. People carefully curate online personas, presenting edited versions of themselves. Social media environments have their own rules, algorithms, and power structures. Users increasingly live dual lives, online and offline, with the online version sometimes feeling more real or more important. This experience of living in mediated, curated, algorithmically determined digital spaces might prime people to accept simulation theory. The simulation hypothesis has also influenced how some people think about ethics and responsibility. If we might create conscious simulations in the future, how should we treat simulated beings? This question has parallels to debates about AI rights, animal welfare, and moral consideration for non-human entities. If simulated consciousness is real consciousness, then causing a simulated being to suffer would be morally equivalent to causing a biological being to suffer. This connects to concerns about the ethics of our potential simulators. If we're in a simulation, the beings running it have enormous power over us. Are they ethically obligated to intervene when we suffer? Should they let the simulation run naturally even when disaster strikes? These theological questions, why does God allow suffering, get reframed in computational terms. Some people have even suggested we should try to please our simulators, to make ourselves interesting or valuable enough that they keep the simulation running. This is cosmic anxiety repackaged, the fear that we exist at the whim of incomprehensible powers that might decide we're no longer worth the computational resources. It's divine judgment reimagined for the digital age. Here's the central frustration with simulation theory. Even if it's true, proving it might be impossible. And even if it's false, disproving it is certainly impossible. We're trapped in an epistemological puzzle box, trying to determine the nature of reality, using tools that are themselves part of that reality. It's like asking a character in a novel to determine whether they're in a novel by examining the pages they're written on. Except they can't see the pages, only the story. Let's start with what proof might look like if we could obtain it. The most dramatic evidence would be discovering obvious artifacts of simulation. Glitches, code fragments, messages from the simulators. Imagine if physicists discovered literal lines of code embedded in the structure of spacetime, or if we found a cosmic made by signature in the cosmic microwave background. That would be pretty compelling. But there's a problem with this scenario. If our simulators are competent, they presumably don't want us to easily discover we're simulated. Any obvious evidence would likely be a bug, an error in the simulation's implementation. And if it's a bug, they could fix it. The moment we discovered incontrovertible proof, the simulation could be reset to before that discovery, or the evidence could be patched out. We'd never know what we'd briefly found. This is the problem with searching for glitches. Even if glitches exist, they might be self-correcting. Any anomaly significant enough to prove simulation would likely trigger debugging protocols. The simulation would crash and reload from a save point, or the problematic code would be patched. From inside the simulation, this would be undetectable. Our memories would be reset along with everything else. Some physicists have proposed looking for more subtle evidence. In 2012, physicists at the University of Bonn suggested that if our universe is a numerical simulation running on a cubic lattice, there should be detectable irregularities in the distribution of ultra-high-energy cosmic rays. These particles should show a slight preference for certain directions aligned with the lattice structure. The idea is clever. Most optimization strategies for simulating physics use lattice structures, discrete grids rather than continuous space. These lattices introduce subtle directional biases that wouldn't exist in truly isotropic spacetime. If we could detect these biases, it would suggest an underlying computational grid. So far, experiments haven't found such evidence. Cosmic ray distributions appear isotropic, the same in all directions, at least within our current ability to measure. But absence of evidence isn't evidence of absence. Maybe the lattice is too fine-grained for us to detect. Or maybe our universe uses a different computational architecture that doesn't introduce directional biases. Another proposed test involves looking for computational limits. If the universe is simulated, there should be maximum information density, maximum computational complexity, maximum precision in physical quantities. We might find places where nature seems to cut corners, where calculations appear to be done in finite precision rather than infinite precision. Some physicists point to quantum mechanics itself as evidence of such limits. The uncertainty principle could reflect computational constraints. The simulation doesn't need to compute exact position and momentum simultaneously, so it doesn't. The quantization of energy levels, the discrete nature of particle properties, the Planck scale limits on space and time. All could be interpreted as evidence of underlying discretization, of a fundamentally digital rather than analog universe. But here's the problem. These features of quantum mechanics could be fundamental to reality rather than artifacts of simulation. Maybe base reality itself is quantum and discrete. Maybe the universe we're in isn't simulated, but is the fundamental level, and it just happens to operate in ways that look computational. We can't distinguish between this is how simulations work and this is how reality works when we only have one reality to examine. There's also a detection problem related to scale. If we're in a simulation, the simulation might only render in detail what's actually observed. Everything beyond our observational horizon might exist only as probability distributions or simplified models. But this means we can never detect the boundary of the rendered region, because the act of looking would cause that region to be rendered in detail. This is like the game design principle of fog of war. Areas you haven't explored yet are hidden, but when you move toward them, they become visible. From inside the game, you can't tell whether those areas existed in detail before you arrived or were generated as you approached. The simulation would always appear consistent and detailed wherever you looked. Similarly, we can't prove we're not in a simulation by observing distant galaxies in detail, because the act of observation might be what causes those galaxies to be computed in detail. Before we looked, they might have existed only as statistical placeholders. After we look, they're fully rendered. We can never catch the simulation being lazy because it responds to our observations by being thorough. This is related to the measurement problem in quantum mechanics. Before measurement, quantum systems exist in superposition, multiple states simultaneously. Measurement causes collapse to a single state. If we interpret this through simulation theory, measurement is the trigger that causes the simulation to compute a specific outcome, rather than maintaining the computational efficient superposition state. But this interpretation is unfalsifiable. Whether superposition is a fundamental feature of quantum reality or a rendering optimization in a simulation, it looks the same from inside. We can't perform an experiment that distinguishes between these possibilities, because any experiment is itself part of the system we're trying to examine. Philosopher Bostrom himself has acknowledged this problem. In later writing, he notes that simulation theory might be inherently untestable. If the simulators want us to believe we're in base reality, they could ensure the simulation is perfect. No detectable glitches, no accessible evidence, nothing to reveal its nature. And if they want to remain hidden, we have no way to force revelation. There's also the nested simulation problem. Even if we found proof we were in a simulation and somehow contacted our simulators, we'd face a new question. Are they in a simulation? If it's simulations all the way up, we could never reach base reality. We might communicate with beings we think are in the real world, only to discover they're uncertain about their own reality status. This creates an infinite regress problem. How could any being ever be certain they're in base reality rather than a simulation? Even beings that created us in a simulation would face the same epistemological uncertainty we face. Certainty about reality's fundamental nature might be impossible at any level. Some philosophers argue this makes simulation theory unfalsifiable and therefore unscientific. Karl Popper's criterion for scientific theories is that they must be falsifiable. It must be possible, in principle, to prove them wrong through observation. If no conceivable observation could disprove simulation theory, then it's not a scientific hypothesis, but a metaphysical speculation. But others counter that simulation theory is at least probabilistic. Bostrom's argument doesn't claim certainty, but assigns probabilities to different scenarios. If most civilizations that could run simulations do run them, then we're probably in one. That's a probabilistic claim that could, in principle, be updated based on evidence about the likelihood of technological extinction or the fraction of civilizations that choose to run simulations. We might also find indirect evidence by learning more about consciousness. If we discover that consciousness requires quantum effects that can't be efficiently simulated, or if we find that consciousness has properties that seem incompatible with computational implementation, that would reduce the probability of simulation theory. Conversely, if we successfully create conscious artificial intelligence and demonstrate substrate independence of consciousness, that would increase simulation theory's probability. The philosophical status of simulation theory is genuinely weird. It makes testable predictions. We should see rendering optimizations, discretization, etc., while simultaneously explaining why those tests might fail. The simulation could be arbitrarily good. It's based on logic and probability while being ultimately unfalsifiable. It's empirically motivated based on technological trends while being metaphysically radical. Some philosophers embrace this weirdness. They argue that not all meaningful questions need to be empirically decidable. The simulation question might be inherently undecidable. We can never know for certain, but it's still worth asking because it reveals important things about reality, knowledge, and consciousness. Others take a pragmatic approach. Does it matter? If we can never know whether we're in a simulation, and if the simulation is good enough that it makes no practical difference, then why care? This is essentially Chalmers's position. Simulated reality is still real reality. So the question of simulation becomes philosophically interesting, but practically irrelevant. But there's a counterargument to pragmatism. If we're in a simulation, and if we could somehow communicate with our simulators, that might change everything. We might ask them to modify the simulation, to eliminate suffering, to extend our lives, to grant us capabilities we don't naturally have. We might negotiate our status, requesting better treatment or threatening to do things that make the simulation less interesting if they don't comply. This is cosmic bargaining, trying to game the simulation by making ourselves valuable or threatening to our simulators. Some people have seriously proposed this. They suggest we should make our civilization as interesting as possible to increase the chances simulators keep us running, or that we should search for ways to communicate with beings outside the simulation. But this assumes our simulators care about our preferences, can be bargained with, and have reasons to accommodate us. It's theology in technological language, prayer reimagined as messages to system administrators, divine favor as maintaining computational resources, damnation as simulation termination. The evidence problem also raises questions about skepticism generally. If we can never be certain we're not in a simulation, we also can never be certain about other radical skeptical scenarios. That we're not brains in vats, not dreaming, not deceived by Descartes' demon. Simulation theory is just the latest version of ancient skeptical worries dressed in modern technological terms. Maybe the right response is neither certainty nor despair, but epistemic humility. We probably can't know with absolute certainty what level of reality we occupy. We might be in base reality, or a simulation, or a dream, or some state we can't even conceptualize. But we can still reason, observe, learn, and make decisions based on our best understanding of the evidence we have access to. At the heart of simulation theory lies a question so profound it might be unanswerable. What is consciousness, and could it be simulated? Everything else in simulation theory depends on this. If consciousness can't be computationally implemented, if there's something special about biological awareness that no amount of processing power can replicate, then the entire argument collapses. We might be surrounded by simulated reality, but we couldn't be simulated beings experiencing that reality. Let's start with what philosophers call the hard problem of consciousness. Neuroscientists have made enormous progress understanding the brain, mapping neural circuits, identifying neurotransmitters, tracking information flow through cognitive systems. This is the easy problem, though it's not actually easy. Explaining how the brain processes information, controls behavior, responds to stimuli. But the hard problem is different. Why is there something it feels like to be conscious? Why does seeing red have a particular subjective quality? Why does pain hurt in that specific awful way? Why is there an inner experience at all, rather than just information processing happening in darkness? This is the problem of qualia, the subjective, qualitative character of experience. When you look at a sunset and experience that particular feeling of beauty, something is happening in your brain. Neurons firing in patterns, dopamine releasing, memory systems activating. Neuroscience can, in principle, map all of this. but can it explain why those neural patterns feel like something from the inside? Can it explain why you're having an experience rather than just processing information unconsciously? This matters for simulation theory because if consciousness requires something beyond computation, some special property of biological neurons, some quantum effect, some non-physical soul or spirit, then simulated beings couldn't be conscious. They might behave identically to conscious beings, passing every behavioral test, but they'd be philosophical zombies, entities that act conscious without actually experiencing anything. If that's true, then we can't be in a simulation because we're definitely conscious. We have subjective experiences. There's something it feels like to be us. So either consciousness can be computationally implemented or we're not in a simulation. Most neuroscientists and philosophers of mind lean toward consciousness being substrate independent. The argument goes like this: neurons are just physical systems following natural laws. There's nothing magical about them. They're complex, but they're ultimately just electrochemical processes. If consciousness emerges from these processes, then any system that replicates those processes should also be conscious. This is the principle of multiple realizability. Just as software can run on different hardware, the same program on different computers, minds might be implementable in different substrates. Consciousness might not care whether it's running on carbon-based neurons or silicon-based transistors, as long as the functional relationships, the information processing patterns, are preserved. But here's where it gets philosophically tricky. How do we know if an artificial system is actually conscious rather than just behaving as if it were conscious? This is the problem of other minds, and it applies to humans too. I can't directly observe your consciousness. I infer it from your behavior, your reports of experiences, and the fact that you're physically similar to me and I'm conscious. But this inference becomes uncertain when dealing with artificial systems. A sophisticated chatbot might produce text that sounds conscious, describing feelings, claiming subjective experiences, passing conversational tests. But is it actually experiencing anything or just processing patterns? How could we tell? Philosopher John Searle's Chinese room argument addresses exactly this. Imagine a person who doesn't understand Chinese locked in a room with a massive rulebook. Chinese characters come in through a slot. The person follows the rules to produce response characters and sends them out. From outside, it appears the room understands Chinese. It gives appropriate responses to questions. But nobody actually understands Chinese. The person is just following rules mechanically. Searle argues that computers are like this. They manipulate symbols according to rules without understanding what the symbols mean. A computer running a consciousness simulation might produce all the right outputs without actually being conscious, just as the Chinese room produces correct responses without understanding. But critics counter that this misses the point. Maybe the person in the room doesn't understand Chinese, but the whole system, person plus rulebook plus process, does understand. Similarly, maybe individual neurons don't understand anything, but the brain as a system does. Consciousness might be an emergent property of complex information processing systems, regardless of whether the individual components have understanding. This debate has gone on for decades without resolution, but it matters for simulation theory. If Searle is right and computation alone can never produce consciousness, then we can't be conscious simulations. But if his critics are right, and consciousness emerges from any system with the right functional organization, then consciousness could be substrate independent and simulation theory remains viable. There's another angle to consider. What if consciousness in a simulation is real consciousness, but different from biological consciousness? Maybe there are multiple types of consciousness, implemented differently, but all genuinely experiential. A simulated being might have experiences that feel completely real to them, even if those experiences aren't implemented the same way biological experiences are. This connects to questions about artificial intelligence. As AI systems become more sophisticated, producing increasingly human-like responses, we face practical versions of these philosophical questions. If an AI system convincingly claims to be conscious, reports having experiences, pleads not to be shut down, how should we respond? Do we have moral obligations to possibly conscious artificial systems? Some researchers argue we should err on the side of caution. If there's even a chance that sufficiently complex artificial systems are conscious, we should treat them as if they might be, because the moral cost of being wrong, torturing conscious beings, outweighs the cost of being overly cautious, wasting resources on unconscious systems. Others maintain that current AI systems, however sophisticated their outputs, are clearly not conscious. They're pattern matching and prediction systems, not experiencing subjects. But where's the line? At what point does information processing become complex enough, integrated enough, self-referential enough to produce consciousness? Integrated information theory, proposed by neuroscientist Giulio Tononi, offers one answer. This theory suggests consciousness is identical to integrated information, roughly the amount of information generated by a system beyond what's generated by its parts independently. The more integrated information a system generates, the more conscious it is. This theory implies that consciousness is gradual rather than all or nothing. Simple systems might have tiny amounts of consciousness. Complex systems like human brains have much more, and critically, the theory is substrate independent. Integrated information could be generated by biological neurons, electronic circuits, or any physical system organized appropriately. If integrated information theory is correct, then consciousness is inherently computational. It's about information processing and integration, which means it could definitely be simulated. Moreover, we could potentially measure how conscious a system is by calculating its integrated information, giving us an objective test for consciousness. But other theories of consciousness emphasize different aspects. Global workspace theory suggests consciousness arises from information being broadcast across multiple brain systems simultaneously. Higher-order thought theories propose that consciousness requires thoughts about thoughts, self-referential metacognition. Quantum consciousness theories, though controversial, suggest quantum effects in neurons might be essential. Each theory has different implications for whether consciousness can be simulated. Some are clearly compatible with substrate independence. Others leave room for doubt, and we don't yet know which theory, if any, is correct. There's also the question of simulated beings' moral status. If we create conscious simulations, and we might have moral obligations to do so if we run ancestor simulations to give our ancestors a form of continued existence. What do we owe these simulated beings? Do they have rights? Can we shut down the simulation? Is creating a simulated being who will suffer morally equivalent to creating a biological being who will suffer? These aren't just abstract philosophical questions. As we develop more sophisticated AI and potentially move toward running detailed simulations, we'll face practical decisions about how to treat potentially conscious artificial entities. The simulation hypothesis forces us to think about these issues now, before we're in positions of being simulators ourselves. Here's a strange thought. Maybe consciousness is the whole point of the simulation. Maybe our simulators are interested specifically in studying consciousness, how it emerges, how it functions, what it experiences. We might be consciousness experiments, running to generate data about subjective experience under various conditions. Or maybe consciousness is accidental, an emergent property that the simulators didn't intend, but that arose naturally from the complexity they built into their simulation. They might not even realize we're conscious. We might be like NPCs in a video game that unexpectedly became self-aware, experiencing our programmed existence from the inside, while the players and programmers remain unaware of our inner lives. This raises uncomfortable questions about suffering. If we're in a simulation and we're conscious, then our pain is real pain, our suffering is real suffering. Do our simulators have ethical obligations to minimize this? Should they intervene when disasters occur? Or is the whole point of the simulation to see what happens naturally, in which case intervention would defeat the purpose? These are the same questions we ask about God and the problem of evil, reframed in computational terms. If an all-powerful being created our world, why does suffering exist? If all-powerful simulators created our reality, why don't they fix obvious problems? The answers might be similar. Free will requires non-intervention, suffering serves developmental purposes, or perhaps the creators aren't all good, just all-powerful. So here we are at the end of our journey through simulation theory, and we still don't know. We can't know, might never know, whether we're living in base reality or a computed simulation of reality. The evidence is ambiguous, the logic is sound but unfalsifiable, and absolute certainty seems permanently out of reach. The question is, does it matter? How should we live with this uncertainty? Let's start with the most practical question. If we discovered tomorrow that we're definitely in a simulation, should anything about your life change? Would you quit your job, abandon your responsibilities, stop caring about other people? Would the knowledge that reality is computed, rather than fundamental, make your experiences less real, your relationships less meaningful, your choices less significant? Philosopher David Chalmers has argued persuasively that the answer should be no. If we're in a simulation, the simulation is our reality. The people you love aren't just simulations. They're people implemented in software rather than wetware, but people nonetheless. Your experiences aren't just code. They're your actual experiences, the only experiences you have or can have. The question of substrate becomes irrelevant to lived reality. Think about it this way: you already exist in a mediated reality. Everything you experience comes through your senses and is processed by your brain. You never have direct access to objective reality. You only know your brain's representation of it. In a deep sense, you've always been living in a simulation. The simulation your brain creates from sensory data. Learning that there's another layer, that the reality your brain represents is itself a simulation, doesn't fundamentally change your relationship to experience. You're still conscious, still experiencing, still making choices within your accessible reality. The computational substrate underlying that reality might be different than you thought, but your reality itself remains real. This philosophical position, that simulated reality is still genuinely real, helps diffuse the existential anxiety simulation theory might provoke. You're not just anything. Your life isn't meaningless just because it might be computed. Meaning comes from within experience, from relationships and purposes and values, not from the fundamental substrate that implements those experiences. But there's a counterargument worth considering. If we're in a simulation, we exist at the pleasure of our simulators. They could modify the simulation, reset it, shut it down. This introduces a profound contingency to our existence that might seem to undermine meaning. If everything could be erased or rewritten at any moment by external forces we can't control or even understand, how can anything we do matter? But again, this isn't actually new. Human existence has always been radically contingent. An asteroid could strike Earth tomorrow, a supervolcano could erupt, nuclear war could occur. Even individually, we could die at any moment from accident or illness. We've always existed under the shadow of forces beyond our control that could end everything we know. Simulation theory just gives a new name to old precariousness. Instead of God or fate or chaos determining when our existence ends, it's simulators. But the practical situation is the same. We exist in uncertainty. We can't control ultimate outcomes. And we must find meaning within these constraints rather than demanding meaning be guaranteed by external forces. In fact, simulation theory might offer comfort in some ways. If we're in a simulation, there might be a purpose to our existence. We're here because someone chose to create us, to run this simulation. That's more purpose than random materialist universe offers, where we're just accidents of chemistry happening to achieve self-awareness before entropy destroys us. Of course, the simulator's purposes might not align with what we'd want. Maybe we're entertainment, or scientific experiments, or the equivalent of someone's high school coding project. But even purposeless to them, existence is meaningful to us. Prisoners in Plato's cave still have lives that matter to them, even if the puppet masters controlling the shadows don't care about them. There are also practical implications if simulation theory is true. Some people have suggested we should try to make ourselves interesting or valuable to our simulators, to increase the odds they keep us running. This is a strange form of cosmic gaming. Like trying to be interesting to God so you go to heaven, but the deity is a programmer, and heaven is continued processor allocation. What would make a simulation interesting? Maybe achieving technological milestones, developing AI, achieving space travel, solving major problems. Maybe creating great art and culture. Maybe simply being dramatic and unpredictable. Or maybe our simulators value something we can't even comprehend, and all our efforts to please them are based on completely wrong assumptions about what they want. This is theology reborn as decision theory. Do we live for our creators or for ourselves? Do we seek to understand and fulfill their purposes, or ignore them and create our own meaning? These questions have occupied humans throughout history. Simulation theory gives them a new technological framing, but doesn't fundamentally change them. Some philosophers worry that widespread belief in simulation theory could have negative social effects. If people think they're in a simulation, they might care less about consequences, behave more selfishly, take fewer things seriously. Why worry about climate change if the simulation might end tomorrow? Why practice ethics if nothing is real? But this reasoning seems flawed. First, as we've discussed, simulated reality is still real to its inhabitants, so consequences still matter. Second, even if the simulation might end, it hasn't ended yet, and we have no way to predict when or if it will. Living as if nothing matters because the simulation might end is like refusing to eat because you might die tomorrow. Technically true, but practically absurd. Moreover, humans have always believed they might be in some kind of artificial or secondary reality. Plato's cave, Hindu Maya, Christian creationism. Without this preventing them from living meaningful lives and building civilizations. Simulation theory is just a new version of ancient beliefs, and there's no reason to think it would affect behavior differently than those beliefs did. In fact, simulation theory might encourage more ethical behavior. If our simulators are watching and judging, if we're being evaluated on how we handle our world, that creates incentive to act well, to solve problems, reduce suffering, create beauty and knowledge. It's the same incentive structure as believing in a judging God, just with different metaphors. There's also the question of how simulation theory affects scientific research. Should scientists look for evidence of simulation, devote resources to detecting computational artifacts or trying to communicate with simulators? Or would this be a waste of time and money that could be better spent on conventional research? Some argue that searching for simulation evidence is worthwhile because if successful, it would be the most important discovery in human history. Understanding our true relationship to reality would transform every field of knowledge. Even a small probability of success might justify significant resource investment. Others counter that the search is inherently unfalsifiable. We'll never find conclusive proof, so resources are better spent on answerable questions. Moreover, if we're in a well-designed simulation, the simulators presumably don't want us to detect it, so the search is doomed to fail. Perhaps the middle ground is appropriate. Maintain some research into possible simulation signatures, but don't make it a major priority. Stay alert for unexpected evidence, but don't organize science around an unfalsifiable hypothesis. This is similar to how we treat other low-probability but high-impact possibilities, like alien contact or exotic physics. Tonight, we've journeyed from Plato's cave through quantum mechanics and cosmic computation, from ancient philosophy to cutting-edge physics, exploring one of the most profound questions humans have ever asked. What is the nature of reality itself? Whether we're in base reality or nested simulations, whether the universe is computed on silicon or exists as pure mathematical structure, these questions remain open. And perhaps they should. Perhaps the not knowing is part of what makes us human. Creatures who ask impossible questions, who wonder about our place in existence, who refuse to accept surface appearances without probing deeper. Thank you for joining me on this journey through the possibility that reality itself might be virtual. If you're already drifting off, then our mission is complete. But if you're still awake, perhaps another deep dive through one of our previous episodes will carry you gently into slumber. Until we meet again in these quiet hours, may you find wonder in uncertainty, meaning in experience, and the quiet confidence that whether simulated or fundamental, this moment of consciousness, this precious, strange, improbable moment of awareness, is real enough.